Hello. In this video, we are going to learn how to do numerical integration. And there's three different formulas that we can use for numerical integration. So we're going to look at the midpoint rule, the trapezoid rule, and Simpson's rule. So when you're doing numerical integration, this is really an approximation of the area under a curve. You're looking at a definite integral, so an integral with limits of integration on it. And so if I calculate this, I will get the area under a curve. Usually we use this when we don't know how to integrate. So we've gone through all these other methods of integration, but we still might end up with a function that we don't know how to integrate. And so numerical integration is a way of approximating the value of an integral when we can't integrate any other way. So for each of these formulas, there's two things you're going to have to find no matter which formula you're using. You're going to have to find the length of each subinterval, which here we're calling it delta x. And you can see there's a formula for how to find that. And then we're going to have to find the endpoints of each interval. So you need to know each spot. You're taking an interval and you're dividing it up into n number of subintervals. Okay, and you'll be given that n in each problem that you work on. And so we want to figure out, well, what are all those subintervals? Where do they start and stop for each one of these? So you're going to need these values to plug into any one of these formulas, whether it's midpoint, trapezoid, or Simpson's rule. So the first thing you're always going to do with any of these problems is go for that subinterval length, the delta x. And so you're just taking the endpoints, which you get from the limits of integration on your integral, subtract them, and divide by the number of times you want to divide this up, so that n value that you're given. So that'll give you the distance between each one, and then you can just start with a, the lower endpoint, and start adding that delta x, and you just keep adding it over and over until you get every single value, and you make it all the way to the other end of the interval. That's the idea. Now these formulas can be a little intimidating, so we're going to try and break them down and make this as simple as possible, starting with the midpoint formula. And each one of these, they're a little bit more accurate than the one before. So midpoint is your least accurate approximation. And we do this by first finding the midpoint of each subinterval. And so I can do that by taking each sequence, each consecutive xk values, adding them together and dividing by 2. That will give me the midpoint. So if I'm trying to visualize this, if this is my interval that I've sliced up, I'm looking for that spot in between, right in the middle of each one. And once I find each of those midpoints, I'm going to plug them into this formula. So I take the delta x and multiply that by the sum of each of my midpoints plugged into the function f, which is the function inside the integral that you're trying to approximate. So there's a lot of calculator work here. You want to be really careful typing these into your calculator, but that is the idea behind it. You find these midpoints, plug each one into the function, add them up, and multiply by delta x, and that will give you an approximation of that area under that curve. Trapezoid rule is a little bit more precise, a little better approximation. And with this one, I'm still going to need that delta x and all the xk values, but I don't need the midpoint this time. So that midpoint has this extra step of having to calculate these mk's. With trapezoid rule, now there's some coefficients that are showing up. I've got a 1/2 multiplying by delta x. And then you'll notice there is a coefficient of 2 multiplying by all of these f of xk's in the middle. The only exception is the endpoints. So x0, that's always going to be the start of your interval. So the a, if I'm looking at this interval up here, and xn is always going to be the end of the interval, or the b. And so those don't get multiplied by 2, but everything else in between them gets multiplied by 2. And so again, once you find those xk's in the delta x, you plug them into this formula and get your approximation. Simpson's rule is going to be the best approximation, the most accurate. And it's pretty similar to trapezoid rule, only the coefficients are a little different. And I have a 1/3 multiplying by delta x out front. With this one, just like with trapezoid rule, there's no coefficient on the endpoints. And then the points in between, instead of all being 2's, they're going to alternate between 4 and 2. Starting with 4, and it should end with 4. So 4, 2, 4, 2, 4, 2, 4. Something like that, depending on how many subintervals that you're dividing this up 2. And so those are the 3 formulas. Again, they're kind of intimidating, but I'm going to help you show you like the fastest way that I've found to find those xk's, and then it's a matter of just plugging everything into the functions. Okay, so let's look at our first example, approximate the integral using the midpoint rule, and n equals 4 subintervals. So I'm going to take the subinterval, which I can see from this integral is -2 to 3, and I'm going to divide it up into 4 subintervals. And so I have to find the value of each one of those subintervals where it starts and stops. And just a note here, the integral inside is e to the negative x squared, which don't think we have a method for integrating that otherwise. So approximation is kind of necessary on this one. Okay, so first step is finding the length of the subinterval. And so I take the difference of the 2 limits of integration. So 3 minus -2 gives me a 5. And then I'm dividing that by n subintervals, or 4. So I get a delta x of 5/4 right here. Okay, so the next step is to find those xk values that you're going to plug into the function e to the negative x squared. And the first one's always going to be your lower endpoint. So -2 is my x naught. And then to get the next xk value, I just add delta x to it. So I'm going to take that 5/4, add it to the -2. This is where your calculator really shines. Don't bother with trying to add these add fractions and things by hand. It goes much quicker with the calculator, and you're less prone to make a mistake. So if I start adding these, I get -3/4. And then I do it again. Plus another 5/4 gives me 1/2. Plus another 5/4 gives me a 7/4, and I keep going until I get to 3, because that's the upper limit of my interval. And the next one, if I add 5/4 one more time, I end up with 3. So that's where I know to stop. Also, this is my, if I start with x0, my x4 right here is the last one, because I have 4 subintervals. Okay, so if I was doing Trapezoid Rule or Simpson's Rule, I'd have everything I need to start plugging into the formula. But this is Midpoint Rule, so now I have to find the midpoint. So I need to find the value halfway in between -2 and -3/4, halfway in between -3/4 and 1/2, and so forth. So for the first one, I do take the x naught and the x1 and add them together, and then divide by 2. And so when I plug that into my calculator, I got -11/8. Now I could do this with each one. I could do, for M2, I could do x1 plus x2 divided by 2. But really the faster way to do it is to just use that delta x. The midpoints are going to be the same distance apart as the xk's are from each other. So if I just add 5/4, the delta x, to this, I will get the next midpoint, and then the next, and the next, and so on. So this is really the fastest way to get through this. So plus 5/4 gives me a -1/8. Then add another 5/4. It gives me the 9/8. Add another 5/4. It gets me to 19/8. Okay, and if I kept going, I would actually go over 3, which is the top of my endpoint. So I do want to stop there. Okay, so it's time to pull out my midpoint formula and start plugging things in. So I have delta x. I have each of the midpoints. And I know my function from the integral is that e to the negative x squared. So if I start filling this out, my 5/4 goes in place for the delta x, and then I plug each of the midpoints in for f. So that's a more general form of it. And what I'm actually going to have to type into my calculator looks something like this. Be careful with those negatives in the parentheses. You should be typing those parentheses into your calculator to make sure that the negative gets squared. Or just leave the negative off completely, and that'll save you some work there. So this is a good point to pause it and kind of plug all this into your calculator and see what you get. See if you get the same thing that I did. And hopefully I got the right answer too. It's very easy to do a typo here, so it's always nice to have somebody to check with. So I got about 1.7764. 4 decimal places is a good rule of thumb for how far to take it out. And so there is my midpoint approximation. So that's the approximate area underneath this curve from, was it -2 to 3. Okay, so let's take the same example and now do Simpson's rule instead. So we've got the same interval, same function, only now I'm doing Simpson's rule. So all the initial work is the same. The delta x is exactly the same. The subinterval endpoints are exactly the same. The only difference now is I don't need those midpoints anymore that I had to calculate with the last one. And the formula is a little different. Okay, so I got these again, same way as before, just by starting with the lower endpoint and adding delta x until I got to the other end of the interval. Okay, so just a refresher, this is my Simpson's rule formula. So I've got the 1/3 times delta x. And then I'm going to be typing in all those xk's into the function. And the middle ones, everything but the endpoints, are going to alternate between a 4 and a 2 coefficient. So this is what it looks like for this particular example. I have the 1/3 times the 5/4 out front, and then all of my xk's in here with an alternating 4 to 4 in the middle. And so if I plug those values into the actual function from the integral, it looks something like this. Again, a great place to pause the video, type this onto calculator, and see what you get. And I did simplify my fraction out front. Anything you can quickly simplify before typing to your calculator is going to make your life a little easier. And so I got about 1.6843 for this one. And that is how you use the midpoint rule and the Simpson's rule. For a little practice on your own, go ahead and try example 3 here. We want to take this new function and using the midpoint and trapezoid rules and 6 subintervals, go ahead and approximate this integral.